Okay, hello everybody. Welcome to my talk. Goodbye microservices. Hello self-contained systems. Maybe the title may assume that I do some microservice bashing, but I don't want to do that. I just want to show you an alternative architecture style. I'm Simon, and I'm a Java guy. I'm working for 25 years in the Java environment, and I'm an independent consultant in Switzerland and teaching at 2 universities. And also I'm a JUC leader in Switzerland for the location in Bern. So when we look a bit back into history, so I called it the evolution of architecture, I will show you my journey. So maybe you have different experience, but for me it was like until 1999 we had kind of the wild, wild west in software development, at least in the Java ecosystem. So I was not in Java back then. I was working on IBM mainframe computers doing COBOL development. And around that time, I moved to the Java space. And in Java, in 1999, J2E, which is now known as Jakarta E, was introduced. So all the application servers, stuff like that. And what we have then from around 2000, 2010, we had a lot of greenfield projects. So that was a great time because we could use new technology, we could do whatever we want. For example, I was involved in the first online ticketing system for Swiss Railways, and this was really a great project. And then later on, like 2008, 2009, we had the systems in place and we started already with modernization projects, or we had like maintenance, and we had monolithic systems that may cause problem. And then around 2011, Netflix started to talk about microservices. And the problem with microservices is that they were a bit misunderstood in my experience. And on the other hand, you are not Netflix. So who here in the room is working for a company at scale of Netflix? Someone? We have some, right? I don't, because I'm in Switzerland, and Switzerland has around 9 million citizens. So you don't get more than 9 million concurrent users. So in fact, you get way less users. And especially I'm working mainly in so-called business applications. So I'm working for retail companies, e-commerce, wholesale company, and we don't have the load of Netflix. So probably it's not the best idea to adapt an architecture that was built for a complete different use case, right? So when we're talking about microservices, we also had like to find something to blame or why we do microservices. And what happened, people were blaming monolith as a bad thing. But in fact, they were not blaming monoliths. In fact, they were blaming that on the left-hand side. That's a big ball of mud. So they were blaming the systems that were probably created between 2000 and 2010. They evolved, the team changed, they have a lot of technical debt, for example, and that's the problem that they really try to solve. By the way, that on the picture on the right-hand side, that's a monolith, because in 2001 we had an exhibition in Switzerland, and this monolith here was built by Jean Nouvel. Jean Nouvel is a French artist. And the interesting thing about that, the monolith was made not of stone, but of steel. And inside the monolith, there was a beautiful painting from a battle around the place where the monolith was. So that means you cannot judge a monolith if you don't look into the monolith, because a monolith can be something good, or it can be some big ball of mud. Now, what we already agree for many years, so in 1972, this guy here, it's David Parnas, he was a professor at the Carnegie Mellon University, and he wrote a lot of papers about modularity, but not in terms of distributed systems, more about modularity when doing software development component-wise. And what he said in his paper from 1972, he said that modularization is only effective if you slice whatever component into pieces that are then kind of self-contained. And that's probably the most important part of that. And we also did, like when we're building monolithic application, we also do that in a modular way. But as they evolve, they may end up in a big ball of mud. So that's currently the problem. So modularity was always very important. So we have modules that are components, they're interchangeable and have well-defined interfaces. And if you think about microservices, that's the definition of a microservice, right? Maybe in another granularity. But microservices, the biggest problem in my opinion about microservices is not the idea of this architecture style. The biggest problem of microservices is the name, because it starts with micro. And the fact is, micro is completely misleading. So if you ask the people from Netflix, then the microservices are not micro. These are relatively big components, but they just used the term microservices because they want to emphasize that it's something smaller than big, right? But micro is misleading, and it really depends on the scope where you put your microservices. So who knows about domain-driven design or has an idea of domain-driven design? There is a term called bounded context, and the bounded context is kind of a subdomain in your whole domain model where you try to slice a big domain into smaller parts. And usually such a bounded context could be a good candidate to build a microservice from it. And especially if you look at the project life cycle, you should probably design for maintenance and not just for development, because very often you start with a big team, but over time the team will be smaller. And then you have an issue if you have a lot of microservices, for example. And I was once in a talk about microservices from Google, and they told me that they have around 10 developers per microservice. And that's quite a lot, right? So I have projects that are smaller than 10 people. And I once was at the customer, and they had issues with microservices, and they asked me if I could help them. So they more or less had issues with like resilience things. So if a microservice was not available, the whole system crashed. And then, by the way, I asked them, how many microservices do you have? And then they said, oh, we have 20 microservices. And then I said, oh, wow, you must be a huge team. And then they said, no, we are just 7 people. And so they struggled with updating the microservices, with communication issues. So you shouldn't go too small, in my opinion. Other than that, you will add additional complexity. And this complexity is kind of dangerous, because here on one side I have the modularity, and on the other axis I have the distribution. And if you look at the pictures, we can have a modular monolith. So we can really design a monolithic application in a or in a nice way. We could check that. So there are tools like ArcUnit or other architecture checking tools that could check how the application is contained inside the monolith. And you would do the same with microservices. So it doesn't really matter from the modularity point of view if you're doing a modular monolith or microservices. The difference is really in distribution. So one is distributed, the other one is not distributed. But the problem is, if you don't care about modularity and the dependencies, you end up with a big ball of mud. And that's what happens in the year like 2000, 2010, and probably also today. But if you're doing microservices and do not care about dependencies, it gets even worse, because a distributed big ball of mud is probably the worst thing that you can get, because instead of with the monolithic big ball of mud, where you can use any static analysis code tool that you can generate some diagrams that shows you how your application is structured, you can't do that, because you would need something during runtime that will record the requests between the microservices to find out what they really do and how they are connected. So that's probably a bigger problem. On the other hand, this distributed big ball of mud was also a quote from Simon Brown. Maybe you know him, he was here last year. And he said, if you can't build a modular monolith, why should you be able to do that with microservices? So modularity has really nothing to do with the architecture style. It's just a quality that you should have in your application, no matter if it's distributed or not. And here, the most simple example that you usually find in the books, like an e-commerce system, you have a customer service, an order service, and a catalog probably. You will probably end up with a cycle between customer and order because you want to have all orders from a customer and you want to have some orders from all customers, and this will result in a cycle dependency. On the other hand, microservices have another issue, and the issue is distribution. Because there are a lot of problems when it comes to network, so the network is not reliable, it's not secure, it's probably not fast, it adds latency, and so you get a lot of problems. Martin Fowler once wrote in a blog post already like 20 years ago, the first law of distributed object design: don't distribute at all, because you get into troubles if you do that. And there are various ways to communicate, so I call that synchronous, asynchronous, and event-based. So synchronous is one style that is very often used in microservices. You do REST API, GraphQL, or maybe gRPC, but this binds two services very closely together. So it's the simplest communication style from a programming perspective, but on the other hand, it's a very fragile thing to do. And maybe if you're into microservices, you know the microservice pattern from Chris Richardson, and there are these reliable patterns that help you, like circuit breaker, for example, to overcome that problem. Then we have like a style, I call it asynchronous. It's also known as request reply, where you say, okay, HTTP is not a good idea. We bind things too strictly together. We do that over messaging. It doesn't matter if it's traditional messaging or Kafka or any other technology. And you send a request, and then you wait at some point for the response. But the problem with that, that's also not reliable. So what you do if you don't get a response? And I was working once for a telecommunication company, and they had the first set-up boxes. So back in the days when we started with internet television, we had set-up boxes, and you could order them over like a website. And behind the scenes, there was an SAP system, an ERP system, to deliver these set-up boxes. And they decided to integrate that over request reply model. And during test, it worked fine. They decided, okay, we may have a timeout from about 20 seconds, and if after 20 seconds nothing happens, we just send the message again. So is this a good idea? Maybe. But the problem was that SAP is not idempotent, so that means if you send 2 requests, you get 2 boxes. And in production, the timeout was too short, and a lot of customers get 2 setup boxes, and some don't get any because there were no setup boxes left. So that's a problematic, in my opinion, communication way. The best thing, or the most loosely coupled style, could be event-based, where you have kind of business events that do not result in a direct response, but result in a process event later on that may be seen kind of as a result. When we have synchronous communication, we also have kind of another issue, and maybe you know the n+1 select problem from database. If you use Hibernate, for example, you have that mostly because of lazy loading. So that means, for example, in that case, we have 1 request to get the customer, and then we have like n requests to get the orders for these customers. And if you have that on the database side, that may not be too bad, right? Because the latency between your application and the database is often not too bad because they are very close together. But if you move that problem to a microservice and then you have latency over HTTP, then this became worse. And your application may suffer from performance problems because of that issue here. So these are all the problems that you get if you're trying to communicate between services. Now, my talk is about self-contained systems, so maybe we should have a look at various architecture styles. And on the left-hand side, with the monolithic front end, this is something that I usually see if companies are creating microservices for the first time. So they start to modularize the backend and introduce a lot of microservices, but on the front-end side, they just have a monolith, right? And For the backend developers, that's fine because for them it's modular, but for the front-end developers, it's still the same problem, right? And also what sometimes happens is it's called integration database. That's a pattern from Martin Fowler. If you have two microservices and you integrate with the same database, you are also coupling the thing in the database side. So usually when doing microservices, I see coupling on the front-end side or I see coupling on the database side, and just the business logic or the backend is modularized. On the left-hand side, we see the self-contained system. I will talk about that in a minute in depth, but you will see that we have everything in a silo. That's the main difference of that. Now, microservice, self-contained system, has a website, scsarchitecture.org. It was initially introduced by InnoQ. InnoQ is a German company, German IT services company, and there was a person that unfortunately passed away a few years ago. It's Stefan Tilko, and he introduced this architecture style. Now, what are these self-contained systems? The idea is to break a big system into smaller systems, right? Back in the days, we called that, for example, subsystems. So when I was working with the Swiss Railway ticketing system, we did similar things. So that's not a new idea, but it gets revived because of all the discussion about microservices. And the idea of self-contained systems is that you rely if you're doing domain-driven design. So it doesn't mean that you need to do domain-driven design, right? But the idea of the bounded context fit very well with the idea of self-contained system. And if you look at the picture, it's simple. So we have like here 9 systems. So we have a big system and we cut it into 9 separate systems, and that's called a self-contained system. And it's called self-contained system because we have the UI, the business logic, and the data storage in the whole silo that we are creating out of that. Now, what's the benefit of that? The benefit is that we do not end up with a monolithic front end. And the benefit is also that everything that should be together, so in kind of a part of your application, is together, and you don't have a split between front end and back end. So that doesn't mean that the front end can't be like a single page application, right? Because if you read the paper of InnoQ, they propose to use server-side rendering for that or anything else, that you get the single deployment unit, but you don't need to do that. So you could also do kind of a traditional Angular or React application in the front end, but the idea is that this is kind of enclosed and does not communicate with the outside. And the important thing is optional API. So the idea is really to reduce the communication between the systems. And it shouldn't do synchronous communication at all, because if you start to do synchronous communication between self-contained systems, you end up with a big ball of distributed self-contained systems if you do it wrong. So the idea is really to split the application into parts that need no to very few communication at all. And I will show you an example of a current project I'm working in where we have no communication between self-contained systems. And we see that we just move the communication to another layer, but we will see that in a minute. As for microservices, also for self-contained systems, it's very important to have their own data storage. So that means that you also can decide which data storage you want to have. That also makes it easier to migrate your data or your database if you don't have dependencies on that side. Now, when I say that we don't have any communication, how should they communicate? Or how should you build an application out of self-contained system if there's no communication at all? And the idea is that communication happens on the UI side. So the communication really between two self-contained systems is simply a link, for example. And who of you is using Amazon to buy books or any other stuff? If you do that, you use a self-contained systems architecture. Because today it's harder to spot than a few years ago, because if you search for a book, you add the book to the basket, and then you do the checkout process, you will notice that every step in the checkout process looks differently, because these are not the same applications that you're hitting during the checkout process. And if you do that like this, then you have close to no communication between the systems. But if you need communication between the system, you shouldn't choose synchronous communication, you should choose asynchronous communication. So that means that you, for example, send events if something happens in your self-contained system that any other self-contained system could use, or you could do like data replication between the systems, that they really are autonomous during runtime, during deployment, and also during development. So that's really the center idea of self-contained system. Now, if we're talking about asynchronous communication, we also have issues maybe with consistency, because then you have kind of an eventual consistency, not a strong consistency, so you will not have distributed transactions. And this means the guarantees are a bit relaxed, but we will see on the example that I will show you, maybe that's not even an issue. Because if your systems are cut correctly, you don't have the need to change two databases in one business transactions usually, or not at the same time, or it's not needed to have the data at the same or in real time at the same state. So that really depends, so that you have kind of a relaxed, consistent model. That's the idea about that. Now, if we compare self-contained systems and microservices, I made this table, but there are probably more differences to cover. But the first thing that is probably obvious is that the size will change. So microservices are not small, as I said. They may be small, but they must not be small. But self-contained systems are usually larger. So they consist like a part of your application, for example, the product management part, and that's a self-contained system. Based on the independence, self-contained systems are really autonomous usually. Also, the team is autonomous. They can use whatever technology that they want. There is usually no communication or asynchronous communication. So you don't have to decide if you're using GraphQL, REST, or gRPC, for example, because you simply don't do any synchronous communication. On the other hand, if you're doing traditional microservices, I mean, you can also have microservices that do not communicate with each other, or they just communicate over events, for example, and no synchronous communication. But because microservices are usually fine-grained, they must communicate in a way, otherwise they don't make sense somehow. And from the team structure, you also get fully independent teams because you have a vertical slice, and if you really do that on a business way, like with the idea of bounded context from domain-driven design, you really get autonomous teams, autonomous application, and then you reduce the communication between the teams. Because if you're having synchronous calls, you kind of have to decide how to design the API. So do we have the different styles? Maybe if you know bounded context, you have the context map from domain-driven design, and there you have like a published API maybe that the publisher tells how the API looks like, or you have a consumer-driven API. So you have to communicate between the services because you have to define these APIs. And the interface is probably the biggest difference because self-contained systems also own their own UI. And with microservices, you usually don't have the UI attached. The UI is something completely different from that point of view. And deployment, as we don't have no synchronous communication, we can just deploy it, right? So we don't do anything. So we probably disturb the user if we don't have a continuous deployment, but other than that, we don't have to take care about any other consumer, for example, of our services. And if you're doing microservice, depending on what you're changing, you need some orchestration also on the deployment level. So that's basically the idea. And the idea is a bit because there is another trend. I didn't include that here. Maybe you have heard of monolith. So Oliver Trotbaum from the Spring Framework is even building a framework that's called Modulith. And the idea is to build modular monolithical applications, right? But the idea, if you have a big application, probably that's not really helpful because you have a single deployment unit, right? So if you have some problems in parts of your application and you have a monolithic deployment, then you have to deploy the whole application. That will lead to branching and cherry picking and bug fix branches and stuff like that. With self-contained system, we can avoid that because the changes are locally in our self-contained system. Now, maybe the advantage is to conclude that because we are really trying to uncouple or decouple the parts of in our application, we are more resilient. So if a part of the system is not working, maybe it doesn't matter at all. We will see that in the example. They are scalable, so that's the same advantage with microservices because we can scale on the level of self-contained systems. We are open to integration in terms of we have really self-contained systems that we may implement our own, but we also can have third-party systems that also count as kind of a self-contained system. We will see that in the example in a minute. And as with microservices, we are more or less technical independent. We can do our own decisions. I will talk about that later because sometimes this is not an advantage. It really depends on the size of your company where you're working on. So, for example, I don't know if you know Zalando in Romania. Zalando is a big retailer in Germany and also in Switzerland. And they are really technically independent. So each team can decide they want to use Rust or Java or PHP, whatever. They really are free to decide. But if your company is not that big, probably technical independence doesn't make sense. So there's a term called macro architecture. I will talk about that in a minute as well. The good thing about that, compared not to microservices, but compared to monolithic applications, we don't have a Big Bang release, so we can release independently. And finally, and that's very important because usually you don't start in a kind of greenfield project, you usually have to maintain systems. And if they're split into smaller pieces, you can evolve better and don't have to do big bangs. Or if, for example, like Java migration to newer versions or so is locally to a self-contained system. So that's kind of what self-contained systems are. Now, as I said, I'm currently working for a wholesale company. When I was driving from the airport to the hotel, I saw Selgro. And I'm working for Selgro in Switzerland. So it's not Selgro in Switzerland, it's Transgourmet, but it's the same like company ID. So we have like cash and carry markets where usually like, I don't know how it's in Romania, but in Switzerland usually the customers are restaurants or hotels or retailers who go buy their goods there. And we also have a delivery system for the wholesale ERP system. And this ERP system of this company is like 20 years old, around, a bit later, maybe older, 23, something like that. And it's traditionally built on J2E, and the backend and the front end is Eclipse RCP, because that was the way to do it in the year 2003-04. So a lot of applications were built based on Eclipse as a system. And the problem is Eclipse version 3 they are still using, they are stuck on Java 8. So they cannot move away from Java 8. And we can also not migrate from Eclipse 3 to newer versions because this would be too much effort. And the other problem that we have, it's kind of a monolithic system. So it's a single deployment unit. So we put something in production. And if something changes in some parts in the application, we will always have problems with that, right? The domain model of retail or a wholesale company, doesn't really matter, is always the same. It's relatively simple. That's also because it's usually a good example for books. And you have like the goods that flow in that direction and the money that from the customers that comes back. And in the middle, you have some procurement, so you have to buy goods with your suppliers. On the other hand, you sell the goods to your customers. And then you need some processes to distribute your goods or supply the goods. And finally, you have some finance stuff, and that's it, right? So it's the domain is pretty simple, I would say. Internally, it's much more complicated because if you're a B2B company, you tend to have prices per customer. So B2C is much simpler because you have a single price. Maybe you have discounts or something like that. But if you're doing wholesale for enterprises, for example, if you have a restaurant chain, they will negotiate the prices with the customer, and then every customer may have different discounts and so. So finding prices is very difficult in that domain. And what we have as domains, let's say, it looks like self-contained systems already, but it's kind of the domain. We have parts with the inventory, so all the product data, for example, the information about the supplier, about the prices is somewhere in an inventory system. You have a customer system, you have a sales system, that's usually a web shop, or could also be kind of an application that, for example, a call center is using if they can order by phone. Then we have delivery and logistics systems, so we have a planning tool for the trucks, for example, that deliver the goods, and we have logistics software. But maybe you can see it in the bracket. There is, on one side, it's called Bracar, on the other side, it's called WAMAS. These are products. So you don't do that by your own because logistics is more or less a worldwide standard. So you have this warehouse systems, that's always the same. You don't have to build that by your own, but there are also some logistics processes that may not fit in this product, so we have to do that our own. And the interesting thing about that is if you think at the third-party application, this is a self-contained system, right? Because you need some data from your system to put it in, for example, the logistics system, because they need to know about the products, they need the dimensions of the products, the weight of the product. If it's dangerous goods, for example, is very important, or if it must be stored in a fridge or something, that's the point that we need to have there. And we decide to do that self-contained systems-wise, so that's just an illustration. So that's not really the reality because we will get much more self-contained systems by the end. But the concept that we have is that each system has its own UI as defined by self-contained systems, but we have always two databases. So not really two databases, but probably more two schemas to separate data that we get from somewhere and the data that we write. And as you can see, for example, the inventory system has no interface at all because all the data that the inventory system needs is created by the inventory system. But if you follow the green lines there, you see that all the other systems need this inventory data somehow. Now the question is how to do that. There are, in my opinion, two approaches. The approaches that we use, we do data replication. So that means we have a tool, it's called Symmetric DS. It's built by an American company exactly for retail solutions. So they built a system for Dollar General. Dollar General is a very cheap retailer in the United States. They have around 45,000 stores or something like that, and they use that to synchronize the data from the central inventory system to all the 45,000 stores. We at Transgourmet Switzerland, we only have like 40 stores, so much less traffic. But we replicate the data, and what we do, we don't replicate the exact schema, so we build like the interface on that way. So we do a lot of denormalization of the normalized data, because if you need, for example, the product in a web shop, you just need a single record. And probably you don't need that in the database. It would be better fit for Elasticsearch, probably because you want to search for the products. That's the idea behind that. You could also have another style of integration. You could use message sourcing. So you could use, for example, Kafka, and then every change would be published to a topic, and all the services, all the self-contained system could subscribe for these events and update the data. So that's really kind of a way, or depending on how much additional infrastructure you want to add to your application. So that's why we decided to use replication. And also the reason for replication is that the data must not be replicated in real time. Because if some product manager decides to get a new product from some supplier, for example, this process takes around a week until we can sell the product in the store or we can sell it in the web shop. So this really takes some time, and also the remaining data is not that important. By the way, the interfaces to the logistics system is message driven. So every sales get replicated to the warehouse, for example, for the pickup or the picking of the goods for that. Now we have many of this system, or we will have many of this system. We started last year with the project. I would say, kind of a modernization project of that size takes around 7 to 8 years until it's finished. So it's not a big bang. We have to find a way to migrate there. And because the team is not that big, we have to decide on something called a macro architecture. So we have a lot of technical or design decisions that can be done inside the self-contained system. But because we also share the developers, so we don't have stable teams, sometimes team members move to another team, we should have a look that we kindly have the same type of technology that people can move from team to team. And so I said, we have read-only data replication, we have currently active MQ that may change in the future, and we have user interface, and we really link from self-contained system to self-contained system, and for that purpose we are building a link database that we know on which endpoint finally, or on which address the user interface runs. And we also need something like a common design system, because the application for a user perspective should look like a single application, but we want to have that split. And we are using Vaadin. I don't know if you know the framework. It's a framework to build a web application entirely in Java. We use Spring Boot, Oracle database. We have some Camel for integration, and this symmetric TS for the replication. And the application, the new one, so that's a screenshot from our design system, would look like this. And so that's no surprise. So we have usually tables, and we have master detail view when we can edit the data most often. And these here on the icons on the left-hand side are links to other self-contained systems. So when the application starts, it will look up the database, get all the links, and creates the menu. And then you can click there to navigate to other systems. So we need some additional metadata. So what data do we have to change to send to the other application to make that work? And we also need single sign-on for sure, because otherwise you have to log in with all the other systems. And that's it. So you don't really need more. And also the point is, if you look at, going back to that picture, if you look at the users that are working with these systems, you will notice that not a lot of people are working with more than one of these self-contained systems. So probably most of the users at the company would not even notice if it doesn't look the same at all, right? So if there are minor changes in the UI that are not exactly the same, it may probably not be noticed at all. So the components are very important, and that's also why we are using Vaadin, or one reason, because Vaadin is based on web components. So we created many of these web components. So Vaadin comes with like 30 to 50 web components already, but we created our own components that we need kind of for our applications, and we try to also do style guides that the developers try to implement the application in the same way, and we also do reviews. Now the problem is that we are not on a greenfield, so we have to kind of migrate to this new application, and there is a pattern from Martin Fowler. It's called Strangler fig. The Strangler fig is a plant that wraps around trees. Maybe you have seen that picture already. And because this Strangler fig then uses all the resources from the tree in the middle dies. And finally, you still have the structure, but no tree inside. And that's the idea for migrating existing monolithic applications, for example, into microservices or self-contained system or other monolithic system. It doesn't really matter. So we take our application with the Eclipse RCP client, business logic, and the database, and then we constantly move parts of the application to the new system. And we start with the sales system because the master data system, like the customer system or the inventory system, the data is used by many other applications. So there's not just our ERP system, there are other applications around that are sometimes even directly use the database. So we have to wait with these systems to move away until the last minute. Otherwise, we have to adapt also that in other applications. And so we move parts. So move is not correct, right? Because it's more or less a rewrite. So what we try is to rework or refactor the business logic that it can be used in the new system, because it's also Java. But on the front-end side, we can throw everything away. So first of all, the old UI is old, so it's probably not the best user experience. And on the other hand, it's completely new technology. And also the database, we don't want to keep that, because the database is currently around 2,500 no, that's not true, that's another system. Around 1,000 database tables. And they are normalized. And sometimes we don't need the normalization in the data, so duplication of data may be fine in some cases. And we don't want to move that to the new system. And the idea is that finally, when we are done after a few years, then we will have this self-contained system. And from there on, it will be simpler to migrate to new versions or to different technologies, because you don't have to rebuild the whole system, just the part that you really need to do. So to conclude, in my opinion, self-contained system, in contrast to microservices, has an optimal modularity, because one system will then be like a part of your whole application landscape and fulfill a certain purpose with a certain user group. And you just have to do that in the right way. And you have the autonomy of the teams, that's sure. You have reduced dependencies because you don't do synchronous communication. And deployment is simpler because you don't have to care. You can deploy your whole application. And that's the best thing, in my opinion. It will help in modernization projects, because what we are building today will probably be replaced in 10 to 20 years from now on. Cool. That's it from my side.